So last week we talked about the response of a single degree of freedom system. Free vibration. When we talk about free vibration, that means the external load is equal to 0. Since there is no external load. So, how vibration starts? How does vibration start?
Initial expression, and that's it.
Okay.
You push on a swing.
Yes. Good. So then, initiation of that vibration is due to whether you induce a initial displacement for the mass from its initial location, or you induce a initial velocity for the mass, or at the same time you induce both the displacement and velocity there, so that we should be able to solve the differential equations as shown on top of the screen over here. And we can get that response, displacement response. So we use UT to represent the variation of displacement as a function of time. So that's it is related to the initial displacement. We use U0. So this is the displacement when time t equal to 0, and also related to the initial velocity, we use U0 dot. So for omega n, the omega n, that's a natural angular frequency. It can be calculated as square root of k over n. And so as you can see here, based on the solution of the differential equation, we can tell the amplitude of the displacement here, as well as the areas and the frequency here. So that's the, I would say that's the first problem that we have solved so far for single degree of freedom system without any damping, And before we move forward, any questions regarding the materials we covered last week? Are these in good shape for your homework? So, and this time we will talk about another case that means free vibration. We will talk about the of single degree of system with damping and we first damping first. So basically, tonight we will go over the equation of motion firstly, and we see what would be the solutions to the equation of motion if there is damping for the single degree of freedom system here. And also introduce you some application solutions to the dynamic equations here. And besides the free vibration of the system with the viscous damping, we will also talk about the free vibration of system with Coulomb and damping. So that's a different damping from the viscous damping. We will soon get into solutions to that type of system there. So firstly, what is viscous damping? Viscous damping. So when we talk about the viscous damping, we mean that the damping force, so the FD is proportional to the velocity of the system there. And that means that when we have a go back to the spring mass system here. And so besides the spring and mass, we also have a damping. See the this is the spring. This is the damper. So we have the damping coefficient as C. So so where does the damping come from? Actually, even nowadays, the cause of damping is typically due to, for example, for structures. The cause of damping may be due to the friction between different components, such as in wood frames, between wood beams and the columns, contribute to the primary damping over there. Or the damping may be induced due to the plastic deformation of the structure, such as if you have a steel frame, at some locations the steel may yield or may fracture so under dynamic loading or under vibration. Those type of plastic deformation will contribute to the damping of there. So typically we start from the easiest case where we have the viscous damping, because the damping force can be expressed very easily as a function of velocity and the damping coefficient here. And or you can imagine there is a damper here. What is a typical damper here? Such as if you have a tube here, you fill the tube with some oil. So the oil can create some, because the oil is very high, comes with very high viscosity, so that when the mass moves backwards and forwards, the oil will provide some. So that's how we model the damping. So if we have damping, basically we have to the equation of motion is a little bit different from the case where we do not have damping. So that should be, and we discussed that last week. So you need to here with us your thoughts about how will the equation of motion in this case. The equation of motion here. We talk about that. Yes, Hunter?
The M.
Okay, so the inertial force.
Yep. Plus the stiffness of K times G.
Okay, so plus the spring force.
Yes.
And the three. So when we talk about free vibration, we just the internal force equal to 0. So that's the equation of motion where we have the viscous standing. Any questions up to here? So you should be able to formulate the equation of motion by using the frequency diagram, and then you can take a note with the last week. And so today our goal is to find out the solutions to this equation. This is so all of you have already taken the differential equations, so I'm just going to give you the solution sequence. So when we solve this equation, the first step we need to do a mass. And we need to do some mass normalization. Okay, so that means we divide the mass on both sides of the equation, and so we will have an equation like this. So that's a very easy, very simple math. So now we introduce a very important parameter for time system here. So we introduce a Greek matter. Who knows the pronunciation of this? Theta? Yeah. So the pronunciation should be when I the theta, yeah. Theta that's equal to, then we introduce a new C over. This is called damping ratio. This year, COVID-19 helped us to review some Greek numbers, Greek letters. Omicron. So if I have that theta equal to that C over 2 times m times omega n, and we should be able to have C over n that's equal to 2 times omega n times theta.
Excuse me.
HM, yes.
Sorry, what's omega n again? The natural frequency?
Yeah, omega n, that's the natural frequency here.
Natural.
Yeah, omega n, that's the natural frequency equal to the square root of A over n. So through that whole semester, omega n, that's a natural frequency for undamped system. Undamped system. So if we do this, with the equation 1 should be rewritten as the acceleration plus so we will have the equation of motion expressed in terms of the lateral frequency of undamped system as well as the damping ratio as well as the damping. Good. So any questions up here? Okay. So as you can see here, we introduced the theta here, the theta here. So we have the theta equal to C over 2 times n times omega n. So that's a ratio. That's a ratio. So that's why we also define another important parameter here. That's called the critical damping coefficient. Damping coefficient. So we have that C sub CR that's equal to 2 times m times omega n. Equal to 2 times P over n equal to 2 times. Or this is a critical damping ratio. Critical damping ratio. This is very important, as you can see here. The critical damping ratio is independent of the other parameters. The critical damping ratio is only related to the mass and the stiffness of your structure. So given the mass and the stiffness of the structure, the critical damping ratio is determined. It's determined. It's a determined number. It's a determined number. If we know the mass and the stiffness here. So that would be very helpful when we solve this equation. When you solve this equation.
For CR?
Yeah, C sub CR, C sub CR, critical damping coefficient. So now we will have 3 types of motion after we define the damping ratio here. So when the damping ratio is smaller than 1, so the system is under damped. And so we have to look into 3 different cases. But if you remember when you solve the differential equation on top of the screen over here, you have to formulate a quadratic equation to find out the eigenvalues for that. So the eigenvalues is dependent on the empty ratio number. So that's why we need to do this. And I would encourage you to refer to your textbook. Your textbook includes some derivations, solving the equation of motion there, or you may refer to your calculus to see how you can solve the equation on top. But for this class, since our focus would be the application here, so we will not go into the details on how we solve this problem. So how about the solution here? So we can just go ahead and just give you solutions here. First thing, let's look at the underdamped case. Underdamped single degree of freedom system here. The solution here is so if we have damping on the solution, the version of the solution is a bit more complex, where we do not have any damping. So basically, if you let's take a look at the form of this expression here. So in the parentheses, we have the displacement, initial displacement times cosine omega d t plus sine omega dt times a term related to the initial velocity as well as the initial displacement. So basically, the term inside the parentheses is the sine. And then amplitude is different from the case. We do not have any. And outside the parentheses, we have a term. So this term is increasing. function over here. So with time goes, number outside of the parentheses will be smaller. So that makes sense that with time goes, the system will be the vibration of the system will be terminated eventually because of the existence of the damping. So if we show the shape of the function, we will show that displacement will plot the displacement in the time domain. Basically, we will have something like this. The amplitude decreasing each so where we have the area of the system is ED is equal to so even the amplitude of the system is decreasing, the period is constant. Time for each full cycle, the duration of each full cycle is constant number. So that's how we show the displacement response as a function of time. So any questions after here? We can try again. So remember last time we have a system here. So this time, for example, we can have a mass equal to 1, 2, and then the speed is equal to 1, so that we will have the natural frequency equal to 1 radians per second. And then so we keep the brightness here and damping. This is damping ratio. Right? Talk about the under damped system. Have a number smaller than 1. How about the damping ratio equal to 0.1? Right? So let's say what we have here. So we induce a initial displacement. How about Q? So the system will be, so we can check that this. We introduced the damping, as you can see here. So the amplitudes of the sine wave becomes smaller and smaller. And if the time is infinite, the displacement should be fixed. So this is where we have damping ratio smaller than 1. Eventually, the system here, the vibration is almost terminated due to that. So that's it. So this is if you plot that function using Excel or MATLAB, you should be able to get the same plot as we show here. So any questions up to here? Nothing here, just that. Okay, but for our, in our case, the perspective of engineers, what are we interested? We are interested in the amplitude. So the amplitude of the displacement can tell spring force in the spring. Because for structural engineers, what is our spring?
The building.
The structural frames, beams, brace frames, moment frames, under lateral load, those are the springs for us. So when we design those structure components under dynamic loading, we are interested in their maximum forces in there. So that's why we very interested in the maximum amplitude. The maximum amplitude here. So we should be able to get the maximum amplitude here based on the sine and cosine wave here. So the maximum the amplitude here. So that's given by so that's the maximum. That's the maximum amplitude here. So basically, that's the square of the coefficient before the cosine and the square of the coefficient for the sine term. So just add the square together and you get the square root here, so that you can get the maximum. Displacement response. And another important feature we would like to inspect here is about the effect of damping on the natural frequency of the damped on natural frequency, the damped natural frequency. There is if we plot the ratio between omega and omega as a function of theta, here. So this will be a quarter. And this is equal to 1. And this is equal to And the function of this curve is we have the omega d over omega n squared. And for most of the structures, the theta is smaller than 0.2, smaller than 0.2. So this is a range of MP ratio. Most for most structures, the MP ratio is smaller than 0.2. The question for you is damp versus smaller than the undamped natural frequency or larger? Is omega d smaller than omega n or larger than? So is omega d larger than omega n or smaller than omega n? Smaller, because the omega d over omega n should be smaller, smaller than 1, smaller than 1. And you can also tell from the relation between omega d and omega n. Omega d on the top of the screen here. So the omega d is equal to omega n times square root 1 minus. If you have damping, that means that the natural frequency of the damping system will be a little bit smaller than the natural frequency of undamped. That is very important, very important.
The DM frequency higher than the natural frequency.
Right. For underdamped system there, the natural frequency of damped structure always smaller than the undamped structure. And in the real world, sometimes. So what's a typical, so for example, for steel structures, the typical damping ratio is so for example, steel structures. And typically we can, when you do dynamic analysis, and use the damping ratio equal to 2%. For steel, the damping is pretty small. And for concrete structures, you may use the theta almost. So this is just a approximate value. It's also a function of the structure type. The data, a lot of dynamic testing shows that the ratio is pretty material to use for the check. So this is a solution of the equation of motion for underdamped system here. A little bit investigation of the features of amplitude, the natural frequency here, based on the solution of that equation. And then another thing here is and in your real world, actually, it is very difficult to get the damping ratio. You have to do some dynamic testing. So here, when you do the dynamic testing, you can use the decay of the motion to estimate the damping ratio here. Talk about the decay of the motion for underdamped system here. Yes.
Is there damping ratio for timber?
Yeah, timber. Good question. So for timber structures, you expect a larger number than concrete and steel, or smaller than larger timber structures. You use it. Sometimes you use 10%. Timber structures, you may use a ratio equal to 10%. But that's just a very rough estimation. As I mentioned, the damping ratio is also a function of the structure type. It's not a simple function of the material, also a function of the type of the structure, and also a lot of other stuff. A lot of other stuff. So yeah, actually, to express that the damping ratio mathematically or theoretically is still a very challenging task for scientists. For us engineers, the only way for us to get the exact number is to only based on the testing data we can get the correct. So these two, please keep in mind that these two numbers are very rough estimate. Now for decay of the motion here, very good question. So we can so we know that with damping, So because of the existence of the damping, the maximum magnitude for each cycle. So for example, we have the cycle 1. This is called the first cycle of vibration, and this is a second cycle vibration, where we have the third and maybe somewhere the ice, I plus 1. Gradually, because of the existence of damping, the maximum or the amplitude for each cycle is decreasing. So that, as you can see here, the U3 will be smaller than U2, smaller than U1. So, and we are interested in the decay for 1/4 cycle or 1/4 cycle. So here, and if you look at the displacement at the arbitrary time. So for example, we are interested in the displacement at time t and the displacement time t plus t. So that's the decay of displacement within one cycle. So based on the solution of the dynamic equation, we should be able to get the ut over ut plus td. That's equal to so that means that the displacement at time t, displacement time t plus td at the time after one cycle, ratio between these two displacements is equal to the e's beta times omega n times td. Or we can express that as ext, express that as a damping ratio. So that means that the ratio between the displacement at time and the displacement at time after one cycle can be expressed as a function of the damping ratio. This is very important because with this equation, we can figure out the damping ratio for any structure. Because we can do a dynamic testing, we can excite the structure, we can record the displacement at the mass of the structure, so that we can calculate the ratio here. So we can calculate the ratio here to find out the damping ratio. So specifically here, if we net the U1, U2, UI plus 1, the peaks each cycle. And we should be able to have So the ratio between the two adjacent seats is with the same. Any questions up here? Very straightforward. So this all the derivation is based on the solution, based on the solution. Yes, yes, the same as the so basically this is equal to that's the same. So now we can get the ratio between the first and the any arbitrary one. So for example, the U1 over UG plus 1 should be equal to U1 over U2. A very easy. We have minus here. U1 over UJ plus 1 should be equal to U1 over U2 times U2 over U3, U3 over U4 until we have UJ minus 1 over UJ times UG over UJ plus 1. The reason why we can do this is because U2, U3 will be cancelled, and all of them will be cancelled. So we can expand it. Right? So that's why we can have we know that U1 over U2 that's equal to and how many ratios we have here? We have 8 number of ratios equal to 8. So that means this equal to E and K. And does this make sense? So initially we figure out the ratio between the two adjacent seats. Is that function there. Now we would like to know the ratio between the first peak and the J plus 1 peak. Their ratio should be equal to use the ratio J's order. So very straightforward here. And the reason why we do this is because we can use this equation to find out to express the damping ratio or damping ratio. So if zeta is much smaller than 1, much smaller than 1, we can have the 1 minus theta is almost equal to 1. The difference between square root of 1 minus theta square and 1 can be negligible. Is negligible here. So that means in this case.
So the is critically damped. zeta equals 1 system is critically damped.
Zeta is way less than.
Yeah, the
Oh,
theta is not
right.
equal to 1,
Gotcha.
but the square root, 1 minus theta square is equal. So in this case, we can neglect the term of square root. Right? So that's equal to E. So now we take the log on both sides. We have the log. Yeah. And now we can express theta is equal to that means the theta can be expressed as the log of the ratio between the first peak and the j plus 1 peak over 2 times pi times j. So that's how we can figure out the damping ratio for any single degree of freedom system. Basically, we do a dynamic testing. We do a dynamic testing, which is we here, which is here. If we did not know the damping ratio here, right? We just excite that system to have that system to some vibration here, so that we can measure the displacement here. We can record all the data here. With all the recorded data, we know we have a number for U1, we have a number for UJ plus 1. That's up to you to pick which number of J. J may be equal to 20, maybe equal to 30, maybe equal to 2. So you can pick multiple numbers for J, so that you can do an average. You can do some data analysis to find out the average value of the data. You can have also you can take a look at the statistical properties of the data here. It's on this equation. So that's how we can get the value for the damping ratio. Because as I mentioned earlier, if you would like to find a way to calculate the damping ratio with given the material properties or the geometry of the structure, it's very difficult, very challenging. The only way for us to get the value for damping ratio is to do it. That's why the equation is very important.
For J is just the total number. Peaks. Cycles.
Yeah, J is the cycle. So for example, J plus 1, that's the J plus 1 cycle. For example, you may pick J equal to 1. So this is the first cycle, this is the second cycle.
Right. I guess like I'm just trying to like mathematically put it into a real life situation. Like if I were to say J, we had a system with 10,000 cycles.
Yes.
J at the bottom would be 10,000, but U and U J plus 1.
Okay. So if you have 1,000 cycles, you would like to you may pick J equal to 1,000. And the U1, that is the peak of your first cycle. And you have the data of the displacement. Right? And this is the displacement of the 1,000 cycle. Yes, correct. And let me further explain that here. So for example,
2 pi times 1,000.
so here you do a testing, so that you can record the variation of the displacement of the time. For example, the function of time here. Usually the dance out. So you may pick. So this is U1. So this is U1. This is U1, and your UJ1 can be any one. For example, if you want to pick the typically we do not pick the 1,000. That's because you may pick this 1,000 that will be somewhere here. This is U. One thousand here, 1,000 here. So between the first and the 1,000 displacement, the J is equal to 999, and the U1 and this number should be known to you because that's your testing data. So does that make sense?
Yeah, but what are those U's? Is that like the height from the line of origin to the peak? The amplitude? Sure.
So amplitude. And typically we do not use only 2 data points here. So you may want to use more data points here. So you may also want to use some data points between the 1,000 and the first one here, so that you will have multiple, like based on this equation, you will have multiple, probably you will have multiple values for data, so that you can find out the average or find out the standard deviation or express the data value in statistical. That's how we do that. So that is the only way to find out the value of the image. There is no theoretical. Based on my master's thesis, because when I was doing my master's thesis, I searched a lot of articles from individual. And at that time, I did not find any theoretical way to calculate it. Okay, so let's have a short break and resume the class around 50 past 8. Any questions from Hisham, Patrick, Tim, and Perry? Are you guys interested?
Thank you.
Okay, you are still awake, right? Yeah.
I'll remember in their foundation.
Okay, everyone, let's resume the class. It's okay. We need a very a little bit longer. So so this is how we can solve. We can use this equation to calculate the sampling ratio if we have the testing data. Dynamic testing is pretty easy. You just excite that structure by a lot of ways. For example, you can use a very heavy hammer to hit the one side of the structure frame to make the structure from vibrate, so that you can measure the displacement or acceleration of the frame. As long as we have those information, we should be able to get damping information there. Yeah, because when I was in grad school, I tested a concrete house. I did a dynamic test. I used a small hammer to hit different locations. So it was a very disturbing thing for not a lot of my classmates because that testing setup was very close to an office building. So I did that test for like 3 or 4 days. Had a lot of complaints about the noise that they made. So let's talk about another type of damping. So initially, please keep in mind that the damping ratio here is only for viscous damping, and the equations we used here, the equation of motion, that is only for viscous damping. So the damping force is proportional to the velocity. But we have another type of damping that is also very common, very common. That is called column damping. So,
C number.
is a French scientist or a very famous name in scientific world. That is called column damping. So what is the major difference between column damping and viscous damping is column damping is due to a friction force. For example, if we have a spring mass system, here and so this is the positive direction of the displacement. So this time that the floor or the ground is comes with some friction force. And so if we know the coefficient, if we know that coefficient of friction is equal to mu, So basically, if you excite the system to vibrate because of the friction, the vibration will decay with time going. So this is different. So what is damping force in this case? And the damping force in this case is friction force. Right? Friction. So in order to solve this type of problem, we need to formulate the equation of motion. So we have two cases. This one, motion of mass. motion of the mass to the left, So, then so if the motion of the mass is to the left, what is the direction of the friction force? To the right. So we have this is the mass here. So we will have some friction force here. This is the friction force. And this is equal to mu something mg. And then we have the so the motion equation of motion in this case. The equation of motion in this case is equal to where F is the friction force. Is the friction force. And similarly, and if the motion of the mass to the right, we have the equation of motion. Right. And down. So we have the negative. So, so in this case, we can just go ahead and solve two equations. Solve two differential equations, under than one differential equation for viscous damping case. Right? The solution of this case. So for the case one, the equation one, equation two. So for the equation one, we have UT and C42. A and B, they are constant numbers related to the initial condition. What is the initial condition? Is such as the initial displacement or the initial velocity here. So we need to figure out the values for the constant number A1, B1, and A2, B2 based on the. So that's the solutions. So that the only difference between this case and the viscous damping case is we will have two differential equations because of the direction of the friction force changes with the direction of the motion. So any other questions here? Is everybody interested here? Okay, so now let's figure out what is a constant number. So if we know so if we have an initial displacement to the right, so that means we extend the spring to the right, and we know that initial velocity is equal to 0. And we should be able to have the A1 and the B1 value. The A1 based on the initial condition, we can figure out the values for the constant number. So that we can have the when the time is equal to I over omega n is equal to, if we look at the displacement at the half cycle, at the end of one half cycle, so the displacement here so my question here is, if we know the initial motion is, the initial displacement is to the right, and we can calculate the A1 and the B1, A1 and the B1, right? And so that we should be able to find out that the displacement at the end of the first half cycle, So that's equal to what does that mean? That means if you have so this is where we have the 0 displacement. If we introduce the initial displacement here, so the displacement as a end of that, so this is a t equal to 0. Where when t equal to td, we can get the this is the distance u. So this is the end of the first half cycle. Does that make sense? So because we induced a initial displacement on the right, so the friction force will be to the right, maybe to the right. The friction force is to the right, so that we can use the let me double check. Yes, I'm drawing my notes here. Have you guys noticed the issues here? Oh, right. Right. So as you can see here, because we induce it, we induce the initial displacement on the right. So the spring will pull the mass to the left. The motion is to the left. So that we should be able to use the first equation. So the first equation applies. Because the first equation is formulated based on the motion of mass to the left. So in this case, we should be able to calculate the values for the constant number A1, as well as we can find out the displacement at the end of the first half. And then we can use, and then this mass will move from here to the right, from here to the right. So we can use the second equation. So we use the initial state for equation 4. If we use the displacement, the end of the first half of the initial state for equation 4, because if equation 4 is for the motion from left to right, So we can, in this case, we can calculate the values for A2 and B2. A2 is equal to U0. To get the values for A2 and B2. Does that make sense? Because here for equation 4, the angle of the first half. So when t is equal to circle. We have already figured out the UT here. The UT. And then it's already calculated over here. The minus. So we just go ahead and plug this number in to this equation, so that we can find out the B2 and the B2, B2 and the B2. So we find out the A2 and the B2 numbers here. So now we can combine the both equations, equation 3 and 2. So this is the initial equation for equation 4 and for equation 4, and for equation 3, the initial equation is we have just c equal to 0. The u. Zero. Is the initial equation for equation 1, equation 3, equation 3. And after we find out the values for A1, B1, and A2, B2, we can write the solution here. So we combine equation 3 and the 4, and we will have when E is the so this is the response of the system. The first cycle for the first cycle. Well, the first half cycle and the second half cycle have different functions. We have different functions for the displacement response. Any questions up to here? Okay. So what's the difference between the maximum values of these two values of this? What is the maximum value for the peak value for the first cycle? For the first cycle, u 0. Let's do 0. 0. So we can use this approach for the sequentially for the second cycle, third cycle, and the nth cycle. Sequentially, we should be able to have the relation between the peak value. We will have the peak value. So let's see the decay of the system here. So as you can see here, this is the peak value of the first cycle, and then this is the peak value for the sixth cycle. The peak value always occurs at the start point of each cycle because of the friction will reduce the maximum displacement. So you can see here, based on the derivation here, we can tell that maximum, the peak value for the first cycle and the peak value for the second cycle, the difference will be 4 times F over K. And eventually we have the same relation. So the third cycle and the second cycle, the difference will be the same. So this is a linear decay. This is a linear decay. For so this is different from this process, where we have exponential decay. Here we have a linear decay. This is a very so, and subsequently we can also figure out the response of displacement function of that. Any questions up to here, or please good to for a example here? And let's go over an example here. Yes. Oh, you mean for the viscosity compensation? Typically for okay, very good question. For critically damped and overdamped system, you will see the response over here, such as so for example, if we would like to have an critically damped system, we just change the temperature equal to 1. And then let's see what will happen here. So basically, you will not see any periodic response. With the critical damping, there is we do not have to discuss about the natural frequency because there is no periodic response here. The decay of the motion and occurs very rapidly when the system stops vibration.
Yes, that's what you try to design for, is critically.
You want it, the skyscraper.
Yes, very good insight here. Probably, but it would be very expensive.
So overdamped would be.
Yeah, and now let's see what is overdamped here. Overdamped, we should have a number larger than 1.5. Let's see what 1.5 would be nice. So the system, the motion of the system decays very rapidly, similarly as typically the system. So for typically damped or overdamped system, as you can see here, there is no periodic response here. So we do not have to discuss about natural frequency because there is no natural frequency here. And another thing here is that in the real world, it is very rare to see a structure critically damped because if you have that type of stuff, they have to spend a lot of money. By in this course, get into more detail about critically system. But the textbook, there are some discussions in the textbook. Now, actually, you should be able to. There are two homework problems if you are very interested in the critically damped or overdamped system there. So there are two homework problems here for you to do a little bit derivations here. That's homework 2.9. Let's say over critically damped system 2.9. Homework 2.9. That's about the overly damped system. The vibration decays very rapidly. Very good question. Well, structural dynamics is very rare to have those. It's, as I mentioned earlier, for concrete, steel, or timber structure, the damping ratio is typically smaller than 10%, smaller than 0.1, so far away from the critical damping ratio 1.0. So any other questions? Very good question. Okay, so now let's see a quick example here. So that's about a single degree of freedom system here. So we have so this is a balloon damp system here. So we have a mass device, and so we have the device fixed at the force equal to 10% of the weight. And then natural vibration frequency system is 0.25 seconds. So if this system is given an initial displacement of 2 inches, the release, what will be the displacement amplitude after 6 cycles? And in how many cycles will the system come to rest? So if we use a 2-inch displacement, right? So we induce the initial. Displacement in the 2-inch. And after 6 cycles, what will be the displacement? So we should be able to refer to the conclusions we just talked about a few minutes ago. So what is the difference between so we know that the peak displacement value at the I+1 cycle is equal to its previous cycle minus four times that. That's a conclusion we made. Remember here is have an initial displacement here. After 1 cycle, we will have a smaller one. So we should be able to use this equation. So that means after 1 cycle, so we need to calculate that. Okay, so the F is equal to 1 times W, and what is the K value in this case? We know the natural frequency here, natural period here is 0.25 seconds. So based on the natural frequency, and then this is equal to 2 times pi over m. The higher, the larger the mass, natural frequency. So that we can, and this is equal to. So we can just express the k as a function of the t. We have the this is equal to n over 2, right? This is a k value. This is a k value. And the f over k. Is the 1. And get y over k as a function of g and second. So this is equal to so what is the g value? Inch.
386.
32.4 inch.
That's be precise.
Oh, that's it. Eh? Per second square and we have the 0.25 square and the second square over 2 pi square. Basically here yeah, here. There's something wrong with the unit. This one here. Oh, f over k should be included. Right. Oh, okay, I think that's correct. That's correct. So what number did you get over here? So we got the C. This should be The key we have already expressed the key in terms of the period and the mass. Yeah, we know the unit okay, but we don't have to have the variable key here. Here, the S over P should be input. Okay, my calculator said did something.
My answer is strange. I got 0.010. So that just seems weird. Did anybody second that?
Okay,
Wait,
mass,
Michelle got different.
so now let's work together here. Let's use the scientific formula. We have 0.1 times this one 4 times 0.25. That's 1/4 square. That's we just times 1 over 16 and over 2 over 4 over pi square is about 10.005. We got 0.005 1 foot. And we better change that to inches because the initial displacement is in inches. So we multiply that by 12, and 0.061. One, two, right. So that means that the difference between the first cycle and the second cycle is this. So that means that after first cycle, the displacement we use U is equal to U0 minus U1 minus 2 inches minus that. Oh, 4. Yeah, 4. And 4. So that is after first cycle, after first cycle. So after first cycle, we use the initial displacement minus 1 difference here. So that means after 6 cycles, the U should be U7. Right? That's equal to 2 inch minus and have that means after 6 cycles, displacement will be 2 inches. Does that make sense? Very straightforward. Very straightforward. And similarly, after 10 cycles, plus 1 is equal to this is the after n cycles. Because that to be 0, then that be 0. We can have the n is equal to we get 8.17 if we want to make that. So that means after 8 cycles or 9 cycles here, the vibration stops. And if we have 8 cycles here, this number is larger than 0. So that means that we, after 9 cycles, the vibration. So that's where we have a blend up. Okay. So I'm gonna assign some homeworks for this week. The second homework is due tonight. Okay, very good. Yeah, Hunter submitted his very early. So this time we need to do some calculation of some system here. Okay. So I'm gonna upload the homework numbers on Blackboard. Probably tomorrow morning it would be. I think that's all for tonight. That's all for the brain vibration of equilibrium of system there. So next week we will talk about the vibration of system under external load, harmonic load. For example, if you have a earthquake in a sine wave or cosine wave, or you have a external load induced by your machinery, working of machinery, how will the response of the in that case? And next week we will start with discussion of vibrational system under external installation. So a free vibration. I think that's all for tonight. We have it done earlier. Let me know if you have any questions.
Professor, is the homework due by end of today or by the class time?